So nice to see the chairs filled up. So about me, I'm Jamie. I work at Mibex Software in Zurich, and in my free time, I do like to contribute to Scala open source, and you can see a bit more what I do on social media or my website. So today, I really want to try and motivate what is the real purpose of match types and why you should adopt them, and compare them to the alternative, and then maybe provide some effective tips and troubleshoot some issues that you might have, because basically I think a lot of people have criticized them for being quite complex or not doing everything they need, sort of being half-baked. So maybe we can dispel some fear of that. So to begin, let's set the scene. Can you have a programming language that is both expressive, so lets you write code how you want it to be, and can you also have a safe language at the same time, meaning that the language tries to put stopgaps to prevent programmer error? So with Scala, I believe we can pick two at the same time. But yeah, what am I getting at? So certainly preventing runtime errors is basically quite a hot topic, whether it's the White House telling you to rewrite everything in Rust to prevent memory safety bugs, or you may have read popular blog posts with catchy titles such as "You should pass, not validate," or you probably definitely heard the phrase "make a legal state unrepresentable," which came from a white paper from OCaml at Jane Street. And the point is that to try and avoid these runtime errors, you should introduce more static types into your program. And with static types, of course, you have APIs with stronger contracts, so you can verify, so you can set requirements of what comes in, and you can validate what goes out. And you have invariants that enforce at compile time, which basically means you don't need to defensively program to keep checking that something is in the state that you want. So that's basically dead code elimination, zero cost safety, and you can refactor your code more without fear of regressions. So is there a cost to this static typing? Well, this meme post on the left, which I think had a huge number of views, but 600,000 views, is basically trying to say that, I find Rust so terrible to use because of its scary verbose syntax, and I always have to fight the borrow checker to do anything I want. So that's bad. That's situation A. And then the next situation is, my dynamic programming language Elixir is so wonderful and expressive. There's no boilerplate, and I can even pattern match in the definition. So, wow, maximum expressivity. But of course, we're at the Scala conference. And isn't Scala supposed to be both expressive and safe? And if you read the Scala book, it says Scala has a dynamic feel. So the idea that I'm trying to put forward is that match types are going to give you the expressive power of a dynamic language, but with the safety of static types. So if we put both Ruby and Scala back to back here, this is a very typical example taken from the Sinatra library, which is a library for routing in Ruby. And this is basically a program that says, let's just match request hello / and then some placeholder for a name. And then we're going to respond to the user with hello and then look up the name parameter. But in this Ruby example, this is a dynamic lookup. So perhaps we could make a spelling error, but obviously this example is very small, so no worry there. But with a match type, what we can do is convert this string value into a type-safe structural type, so we can validate at compile time and have maximum type safety that the name parameter definitely exists. All right, so obviously you have to have a demo of that. Okay, so we have our HTTP GET and then the root pattern, and then inside the request my parameters is this sort of structural type that has the name parameter as a real field that I can select. And then I can obviously do multiple parameters in the same root. And perhaps I can even have query parameters. So after the question mark, then these sort of query parameters are repeatable. So instead, I should have a sequence instead of just string. So yeah, this is all achieved with a match type. And yes, I have to go back here. And if you, where's my cursor? So this is all on my GitHub repo, Scala Days 2025. Anyway, so how is this possible? First of all, that white space, that's just syntax sugar for infix method call. So how do we get this structural type name? The first thing is that the parameters is actually not a sort of single object, but it's a method that requires some implicit scope that's provided by this in method. And this context parameter has a sort of structural type, a named tuple, so it has a name field. And then this name field comes directly from the path and is computed with a match type. And there's supposed to be an arrow here pointing from here to here. Oh, there it is. Okay, good. Onwards. So how would you go and design this kind of API? So when we call the get method, it's going to basically construct a builder that will eventually turn into a request handler. And that request handler at runtime is going to read the real URL from the request and extract whatever path parameters match this route into some sort of dynamically typed map or dictionary that we don't really know what's inside of it. Then what we have to do is try and turn this pattern into a type. And we can do that with this simple, this pattern, you just say pattern.type, and then you get, from the value of pattern, you suddenly get the type of pattern. And with a string literal, then you actually get a string literal as a type. And then we're going to use type level programming techniques, such as using a match type, to transform the type of this string literal into the type of this named tuple. And then through some other mechanism, we're going to just assert that the structure of this matches the real runtime map. So this is the actual code. So yes, so the get method is going to construct a get builder. And this is a type you may not have seen, but it's enabled by this modularity import, which is an experimental feature to basically give you the return type of exactly calling the constructor of this get builder. So it's literally like the type of just calling the get builder. And in here, you see it's literally like type get builder equals get builder. So it's a bit redundant to say that. And basically this tracked parameter is preserving the singleton type of this pattern all the way through. Then we pass the singleton type of this pattern to the params of type, which is this match type that's going to extract the named tuple of fields that then gets passed on to in, as I said. And this is how it evaluates. So if I pass in that name root, then you're going to get the name tuple pattern. All right, so that was the motivation of why it's useful for this example. And what do match types really look like? How do you define them? So this is the simplest possible match type you can have. You just have some type, match, and then brackets, and then one-to-many patterns, and then the resolver tries to reduce that match type. So this should give you a link to my website, so you can try this out yourself. So actually on here I have two links. I have the GitHub repo, which is public, and then we have this match type simulator. Maybe make that bigger. Okay. So yeah, everyone can read this on the left. Okay. So we have basic match type here, which is like just pattern match exactly on the type and return it. So if it's ID of int, then as we expect, we might get some int. You can do more complicated patterns. So let's say we want to take a pair of tags, such as this I tag, tag of int, and S tag, which is a tag of string, and extract the little type parameters from them. So you might expect to get int or string. But then how does this actually work? So basically the first step is that the parameter gets passed in here, and that becomes t. So then this t is going to be evaluated as the scrutiny of the match type. So we're going to have this pair of two singleton values. And then the first thing is that we try each pattern in sequence, and we check that the pattern is a subtype of the scrutiny. So is a pair of tags a subtype of these two pairs of singleton values? Yes, it is. So it matches here. And then we have to basically unify the type parameters that exist here with the base type. It's called base type of that. So for I tag, we extend tag of int. So then it should extract x to int, and tag y here is matching on the S tag, which is tag of string. So we get a string here. Good. Yeah, so then it resolves to the right-hand side. So you can have even more funny patterns. You can have a type alias and extract some type members. Yeah. So what if you have more than one pattern? What's happening here? So again, we're going to try, and we have the match type here that's basically going to simulate getting the element type of some sort of collection-like value. So for string, the collection type is char. For empty tuple, there's nothing in it. For sequence and option, it's more clear. It's just the type parameter. So first thing is, yeah, we have to check, is empty tuple a subtype of sum? No, it's not. So then we say, is string a subtype of sum of int? No. Is sequence? No. Option, yes. Option is subtype. So then, like I showed before, we unify the type parameter with the base type, and then we finally get to here. So what if we have something that doesn't match? Like, let's have a future of unit. Okay. So does anyone know what's going to happen? Yes, it cannot be proven to be disjoint. That is the answer. So you wouldn't have thought of this in your worst nightmare, but actually it's possible that you could have a subtype of both sequence and future at the same time. So you could mix them together. So somehow it's a future and a sequence at the same time, but not a sequence of futures. And the reason is because sequence is a trait and future is a trait. So who knows what sort of class could mix them in at runtime. So this is a bit more clear if we have an example like, is it a list or is it a vector? So for a list, obviously, it's list, and for vector, it's vector. And then, what if it's a sequence? And again, it's disjoint. So this seems really annoying and unuseful. Like, why can't it just go to the one that I want? And going back to this element type one, I have to show this. It's because of this funny, it's not funny. There's this feature called dependent method. And maybe we'll really make that big. So for every match type that exists that you can define, there's basically an identical method that is a dependent method on that. Oh, it doesn't work when I zoom in. That's terrible. Oh no, I can't type here. I have to type here, of course. So this is so rigid that it's basically you can mechanically generate it, of course. So the way it works is you have a method, and then as long as its return type is a match type, and then it is a pattern match, and as long as the type of the scrutiny of the match is the same as the type up here of the match type, and the cases are in exactly the same order, and with this type pattern thing, then the right-hand side of each of these cases is actually the same as the right-hand side of this. So it does allow you to do some pretty cool things later, like, for example, if you have GADT reasoning that doesn't really work, you can try with a dependent method on a match type, and maybe that will fix it. But yeah, the reason that we have this disjointness thing with the future, right? So we don't want the future to match is because of this dependent thing. So when we get to, if we were in the middle of this dependent method, then once we get to the sequence, perhaps the T, which is statically future, is actually this sort of subtype that mixes in the future and the sequence at the same time. So then that would not work at runtime. It would go into this case, so that wouldn't be what we want. So we just have to just say we don't know what it is at this point. Yeah, so what other cool things you could do? Say you want to have recursion. You can have recursion, of course, in a match type. So if we wanted to flatten out this option and just get the final bit of int at the end, then, of course, we first check this, and then we're going to say, oh, it is an option, so then we resolve and so on, and we keep shrinking this scrutiny as we go through until eventually the scrutiny is int. Then, of course, int is going to be disjoint from options, so then we get to the next case and finally resolve the output to int. So just for fun, we could do the same with tuple, of course. So then the last element of this tuple list. Yeah, so actually the reason I show this is because when you're doing match types, basically you have to think of this generic tuple as like a list of types. So similar to you have list for values, you have a generic tuple for storing each individual type as an element of a list. So it's useful to, of course, have the same collection operations. Okay, so there are some more rules, of course. If I showed you before, this thing where you could have a type alias and extract the type members, it's illegal to have more than one. At a time, I really would like this to change. I don't know if it could. Probably need a SIP for that, but if it's fine to have one. So just one is fine, two is not, and basically if you want to extract more than one, you have to do this wrap it in tuple and try and do one for each field on both sides. It's also illegal to have a nested pattern if the parameter is invariant. So array is has an invariant type parameter, so then it makes this illegal because I think it's because it can't fully determine what should the x be in here. Of course, it's only illegal if you have a binding. So if it's a list of int, I think this one should match. Yes, that matches. Okay, yeah, other thing you can't do, you cannot try and use it to strip null from a nullable type. So maybe you thought you could do that. Again, because union types are basically unordered, they're just a sort of set of stuff together, then there's no way to pick out one from the other. Same thing with intersections. It's not going to work. Anyway, so that's that. Then the last thing I wanted to show is really this disjointness checking. So I have lots of examples here. So first thing, if you have an abstract type, so one of these things where you just declare type A, then this is literally indistinguishable from anything else in the whole world. It could be anything because abstract type can be then turned into an alias in some sort of concrete class. So perhaps it is string at runtime, no one knows. I showed you this example with two traits. So any two traits like T and U, they cannot be disjoint because this class might exist that mixes both of them. Same with an arbitrary class, like a normal class T and a trait T. It's the same thing. There's some subclass that could exist. I guess if you had whole program analysis, maybe there's one. Actually, I'm Who knows if I'm correct in that, but yeah, if you had whole program analysis, maybe you could prove that this doesn't actually exist, but I think doesn't really go ahead and search for that. But if you have a final class, then of course f can no longer be extended, so therefore it's fine to say that trait t is definitely not going to be mixed into f. Same with objects, same thing. And if you have a sealed trait and a class, then the sealed trait has a known set of children that it knows about, so it definitely knows that one of those is not going to be mixed into C later. And then if you have two random classes like this, then because we have single inheritance in Scala, that means that something, if D did not already extend C, then something can't extend both of those. So these are basically these rules give you a sort of strategy for how to design your match types, because basically you just should never, ever have either an abstract type or a trait, basically an open trait or any open class as a pattern. It's just not going to work. And that even happens like when you try and pass in a type from the outside and try and use it as, was it my argument from the outside? And then it's the same rules there. So some more concrete ones from the actual standard library. So if you have two literal types, they're going to be different. But 42 and int, obviously we don't know which one of those because it's subtyping. Yeah, so empty tuple and tuple, then we know perhaps tuple is going to be empty tuple, so yeah. So like I said, that's on my website, so try and check it out, and you can even like define any custom type you want, so that's quite fun. So just do one with Boolean in here. If we go back to here, then this one. So now it knows about this new type that I defined there. And this is just showing off. There we go. There's a Boolean there. So that was that. And I think I can move on to this now. Does anyone have any questions about the rules? Yeah. Okay. We'll put it in the docs. Yes.
You showed the recursive match types.
Yeah.
Is there a limit to the depth of recursion that can occur?
Yes, it's limited by your stack. And I would hope that in the future we could have some sort of like we have the tail rec optimization for methods. Maybe we could have that for match types in the future, but it's not there now. So yeah, you need a big stack size for big types, which is on my final slide. All right, so next thing. The compiler provides in the standard library several built-in, like intrinsic match types, which are really good for operations on the literal types. So computing with numerics, we have this S thing, which is like the successor. So you can always match on 23 and say it's the successor of 22. You can check equality, you can concatenate strings, and these ones are particularly important for that routing demo I showed. So substring, character at, and length, and these basically help you build parsers for any sort of domain-specific language you want out of a string type. And I'll show more demos later. And then we also have conversions from case class to named tuple type. So that's named tuple from. Yeah, and in general, these live in this Scala compile time ops library, and there's several ones for all the various primitive types and the string type. And next thing, you should definitely make use of the already existing tuple operations that are built in. So generic tuples let you zip and map and flat map as methods. These methods are also backed by types that give them the correct type at runtime. So you can very easily, you don't have to think about the recursion yourself, just use these sort of higher order as higher order operations with lambdas or type lambda. So if you don't know this is a type lambda syntax. So it's basically a type where you have a type parameter, and then this arrow is like the function arrow, but is for types. And then this is a compile time op here. You can also materialize values from your match type results. So let's say you had some sort of algorithm that computed a new value from a literal type. If you use const value, then you can then materialize that as a runtime value. And we also have this one for tuples, const value tuples, so it can convert this result of doubling every value into a tuple at runtime. Okay, so you saw, for example, that recursive. Basically, you can design real algorithms with match types. So if you go crazy with them, what's the cost? So I'm going to use a very canonical example that Scala people know, which if you've ever heard of shapeless, then it's based around this type called the H list, which is like the generic tuple, a list of types. So my question is, how do we, proving that the last element of this very long list is a string. And there's two techniques for that. There's the Scala 2 way with implicits, which I'm not going to explain too much detail, but I have to define some sort of trait with this out parameter, which is like a holder for the type as I compute it. And then I have to define this base case. So I am explaining it actually. So I know for a fact that if H is concatenated to H_nil.type, then H is the output of being last. And then I have an inductive case where, seeing as I know there existed some sort of last for T, then if H is concatenated to T, then whatever was the result of the previous thing is the result of this one. Okay, and the match type version is this one that we sort of saw earlier, but just for H list rather than tuple. And to prove that X is the last of L, then we have to summon this type equality thing, that the last is the same as that. Whereas for the implicits, then it's just the type of this is last thing. And here is the result. So on the left, we have match types. And basically, I did two comparisons. I did one where the list was 200, I think it was 200 elements or 100 elements, and then one where it was 50 elements. Yeah, 50 and 100. So for match types, 100 elements was less than half the time for 50 elements with the implicit version. And then this, who even knows, this is like completely exponential for 100 elements for implicits, whereas it looks like a much more linear growth for match types, but I'd have to validate that by doing a third example. I didn't want to do that. Anyway, so you can see the line is match types way faster than implicits and way less complicated, so good. Yes?
Is this comparison with implicits on Scala 2 or Scala 3? I feel like I remember that I found some...
That's true.
In Scala 3 or something like that.
I did not use the Scala 2 compiler. I used the same compiler, so perhaps the Scala 2 compiler's version of implicit is quicker?
I think it is.
Okay. Well, the benchmark is on here, so you can try it out, I guess. Okay, so that was all the theory. Let's do the fun demos. All right, so when the match type feature was first being produced, we had Maxime from EPFL wrote this very cool validator to wrap TensorFlow with basically shape validation to make sure that, when you try and reshape a matrix that you don't have an incorrect number of elements. So it checks the dimensions basically. So yeah, Python wouldn't do that for you, so there you go. Match types are really good for wrapping dynamic APIs. Same with regex in Scala. So basically, if you try and unapply a regex in Scala, then you just get a sequence of who knows how many match groups. So Olivier, who did a lot of work on the final implementation of match types, did this library regsafe, but it was never published for a stable version of Scala, so you have to use this 3.2.0 RC1, and then you have to use JVM 17 because otherwise it crashes. Anyway, so the good point of this is that it uses, again, a match type to read the string and parse out how many groups there are, and also if the group is optional. So instead of just matching and getting null, we actually get an option where it's appropriate and a null safe string otherwise. And we get precisely the number of groups that exist. So it's just safety and a good demonstration of using those compile time ops. So another example I wanted to show, but I'll show it for real at the end if we have time. But yeah, if you're writing a web form with Laminar, which is alternative to React but better for Scala, I'm not sure if it's the most efficient way to do it, but it's the lazy way to do it for me. So I want to just collect all my form fields in one case class, and I don't want to have to keep defining all my various observables and signals, which are the two primitives of Laminar. I just want to define them in one place, and it has to know exactly how to work for any case class. So I define this var lenses thing, which can take any case class as an argument, and basically it can provide, when I extend, then it basically can provide a lens for every kind of field, each one that exists. And then if I add a new field, then it will suddenly have a new lens. So this is achieved with structural types, and yeah, I talked about that as scalar. And match types basically to wrap each field, the type of each field in this either observer or signal. Yes, that could be confusing. Sorry about that. Yeah, so it was basically like this form that says, yeah, I could show you actually for real. So. Yeah, so it's just a form that asks for your zip code. Yeah, I know that. It is a zip code, according to the Laminar website where I copied it from. So that was this. Yes, I think I have time. So, or do I? I only have 10 minutes, is that it?
5 minutes.
Oh my God.
6 minutes.
Okay, so let's just say I could add an extra field here and it would just magically have a new extension method for me to click on. And yeah, so this is using structural types, which I talked about. So go and watch my talk from Scala, please. A lot more context on these structural types. Yes, and now we can do refined types. Very cool. So if you don't know, refined types, basically a way to prove at compile time that some value matches a predicate. So we could say that this 1 is definitely positive, or we could say that this string should be rejected because it has 9 characters instead of 8 characters. So here's what the positive match type would look like. It goes on the right-hand side here. And the way that works is this implicit conversion that just checks that applying the match type to the singleton type of the value definitely resolves to true, and this is like that type equality implicit that is in the predef. Okay, good. And I also showed before at Scalar that perhaps we could simplify the Scala SQL library. So now we have just a normal case class here, and the companion object extends this simple table thing. And this is a query library to do SQL queries. And basically when you return a row from the database, it's typed as this city thing, but then within the query, it's typed as this record thing, which basically explodes each of these fields into this expression type. So again, this is done with structural types. But yeah, so observe here, the population is long, but here it's expression of long. And yeah, to do that, I have to basically do this complicated match type where I say, oh yeah, outside the query, it's identity type. So I have to pass in this random thing here to detect if it's the identity type, because there's not, there's not a single way to define an identity type. You just test its behavior. So I use this completely obscure internal type that no one would ever know about. And if I return it, then obviously it must be the identity. Otherwise, I turn it into this record thing as I showed. And so then when it's ID, then you get city. Otherwise, you're going to get either wrapping each field an expression or wrapping each field in a column. Internally within a record, then we have this fields type. And basically you have to map each field and check either if it's a nested thing, which is a way to put a case class within a case class and explode the fields of that case class, or just wrap each thing. Then, another use case is, I showed this off at Scala, but for example, this aggregate method, the thing inside here is a named tuple of expressions. So it has this type of a named tuple of expressions, and then I want to extract out the string and extract out the int, and also extract out the column names to get the result. This is basically dependent typing again, but using match types to compute that. And this is, I will not really go into detail on this, but I'm using implicits to basically assert that a match type that extracts those things is a subtype of this R, which is just using type inference driven by implicit search. Okay, so then fun things you could do is be aware that you're not accidentally using that dependent type syntax that you have, because otherwise, if you try and use 0 here, it says, oh, I expected foo of I, because that's what you said. So then you just have to add the extra case. Here's an issue from Antoine, which is basically saying, oh, why cannot I look for traits in this thing? And I think there's literally no answer to this, except if we had a version of match types that don't do this disjointness checking. And that basically means turning off that dependent method mode, or at least the runtime version of that, because that's the only reason we do the disjointness checking. So it would either just be you have to just cast away, just keep casting, and in some cases, I guess that's fine. Just trust me. Okay. Here's another thing. Yeah, like say if you want to try and use a match type to infer some more precise thing for this Boolean, then it really has to be a match type as the return type. You can't nest it in some other type. So then you just have to redefine this in terms of either to make it work. Okay, another thing. Yeah, so it's very fine and all to define a match type like this, but if you try and define a dependent method using the syntax, then this type is actually unsafe at runtime. So this would blow up and actually give you the first element, because whatever you put here is going to match because it's some sort of H list. So the way to fix that is either use an inline method with inline match, which uses the static dispatch. So this is why I think you could have a static version of match type that gets rid of the disjointness checking, and then it would be fine to use with this inline match. Or you have to redesign your entire algorithm to be in a case that only needs one pattern to look at, and then it looks deeper into whatever it finds once you've resolved the outer layer. Because basically in Scala we only have at runtime you only have the class. You can't look inside the type parameters. So anything that depends on a type parameter, you have to basically first assert that you have the outer wrapping class and then take the fields out and look at them separately. But anyway, I have to define this match type in terms of two match types, because otherwise the dependent typing doesn't track. So I could not put a nested match type here. I have to declare it separately. And then that basically means I have to declare a separate method and call that. But anyway, this preserves the dependent type checking, and it's not an inline method here at least. This one's allowed to be an inline because it is just a helper method, so it's fine. And then yes, as you asked, Nabil, yeah, if you have a small stack size, then it could blow up. But this is only happening in your build, so hopefully not at runtime unless you're doing some sort of weird stage compilation. So hopefully on your build would crash, so just improve the amount of stack size you give it. Yeah, I would like to see that there would be a recursive optimization for match types. And that was everything I had, so thank you.
Don't look away. First.
Okay.
I can project. Okay. Hey, thanks. This was amazing. So that issue that I created, I came up with a clever way of deriving opaque type instances for like opaque type aliases, and then Seb responded to me saying this is not possible, and it broke my heart, and I deleted the file with the experiment, and I never came back to it. So I'm still heartbroken about that. But my question was that thing that you showed, because sorry, I was late. Is that using the compiler, the disjointness checker? How does it work? Why do we not have it in metals, and why do we not have it now? So that's my question.
Yeah. This is completely vibe coded. But I did tell it to use the specification. Yeah. No, actually, it took a lot of nursing as well, because I kept giving it more examples and it kept breaking. So I have to say, no, follow this rule. Anyway, I think it could be ported to Scala and use some real proper rules. I would like to see more people use it, so definitely I'll try and do something with it.
One of the first issues that Rob Norris created about match type was like, why do I not see the expansion in the IDE? Because all it says is like, nope, I don't know what that is, and that's it. That's what it says. So this would be amazing to see.
Yeah. Yeah, like a tracing. Yeah. Anyone else?
So, okay. What's dependent about dependent method? Why is it called that?
Yes, because the type of the result depends on the type of the input, basically. So this, like if you passed in empty tuple, then the return type should be nothing, so I guess it throws. If you put in a string, then you have to return char, and it would actually be typed as that when you return. And if I have a REPL open, I could do that.
So the result type depends on the input type.
Yeah, result depends on the input. Oh no, it's okay. It doesn't like me. Sorry.
Well, unfortunately, once again, we're out of time. But thank you, Jamie, very much for this interactive talk.
Yeah.